Phases of matter. Can you name them? I'm sure you learned them in middle school. Give me the names of the phases of matter. Okay, actually I heard more than 3. I heard somebody say plasma. We're not going to talk about that one a lot in earth science, although you do find it in stars. It's a high energy gas, ionized gas. All right, but the 3 that are most common I heard you say are solid, liquid, and gas. So right over here, walk right up. Look at water as an example. Right? Solid water, ice. Right? We've seen that before. Liquid water, we drink it every day. And water is a gas. Right? When you're boiling water, you can see the steam. So if you back up a little bit, look at the steam coming off the pot. Right? There's the gas. So I've got water as a solid, a liquid, and a gas. The phase of matter depends upon the temperature. So the reason that I have a gas over here is because it's on the hot stove. Temperature and pressure are the 2 factors that determine the phase of matter. We'll talk more about pressure in a little bit. What I want you to do next on the bottom of the page of your notes is I would like you to draw models of what a solid, a liquid, and a gas would look like. So if you had bionic vision and you could zoom in inside of this ice cube and see the little particles or molecules that make them up, what you would see is that all of the particles, right, the molecules, are really close together and all lined up. That's a solid. They have a geometric pattern. If you need more time to pause, you can pause it and to draw that diagram on the bottom of your page. How about a liquid? How's a liquid different? Liquid particles are still really close together. They're just not lined up. They don't have that nice geometric pattern. Right, so they have a little bit more mobility. That's a liquid. Again, pause it if you need more time. And a gas. Gas, the particles are the farthest spread out. Right? So the greatest distance between those. They have the highest energy. So you don't have to draw too many to fill in that picture. And that should complete the bottom of that page of your notes. Top of the next page. How does the phase of matter change if you lower the temperature? So for an example, if I take liquid water and I lower the temperature, I put it inside of the freezer. What's going to happen to a liquid if you lower the temperature in a freezer? All right, we know that the liquid will turn into the solid. So if you lower the temperature, right, a gas, the particles will get closer together as the temperature is lowered, as they get colder, form a liquid. And that liquid that I just put in the freezer will turn into a solid as the energy is lowered. Lowering the temperature is the same as raising the pressure. Lowering the temperature, raising the pressure. Notice they're inverse. If you can envision a gas where you can squeeze, increase the pressure, squeeze those particles closer together, you could actually bring them so close you could form them into a liquid. And if I could squeeze even more, put even more pressure, I could line them right up and form a solid. So, lowering the temperature, raising the pressure, gas to liquid to solid. How about if I raise the temperature? Well, that's easy to show. Take the ice cube, raise its temperature. Put it on the stove, you can see the solid turns into a liquid, it melts, and that liquid will turn into a gas. So, raising the temperature, we go solid to liquid to gas. Okay. And raising the temperature is the same as doing what to the pressure, guys? We said they're opposites. So raising the temperature is like lowering the pressure. We'll go from solid to liquid to gas. Good. Okay, next thing we're going to talk about is density of a gas. So as you can see, I'm standing in front of them setting up a hot air balloon. Now if you can hear that, they've got the blower going, they're heating up the air. So when you talk about a gas, like the air in a balloon, the density is affected by the same 2 things that we said affect density. What are those 2 factors that can influence the density? Temperature and pressure. Great. So for the first example, hot air balloon, they're affecting the temperature. They've got that blower on there, heating up the air, you can see that, and increasing the temperature. So as they increase the temperature, what is happening to the density of the air? What is happening to the density of the balloon? Well, look at the balloon start to lift. If it's floating, what is that telling you about the density? Increased temperature, decreased density. Now the question is why? Write an explanation for that. Why is that air becoming less dense, causing that balloon to float? Right? Because as you heat those particles, they move faster, they collide into one another, and they want to expand and spread out. And as they spread out, they fill that balloon. And as they spread out and fill the balloon, there's more space between them. They're not as packed. They become less dense. They float. Any question on that connection? That's number one. Now, increasing the temperature, if you wanted that same change, to have the balloon get bigger and expand, what would you have to do with the pressure? Remember the inverse. Decrease the pressure. That would be like if you're squeezing that balloon to let go of it, and now it will expand on you. So increasing the temperature, decrease the pressure. What about example number 2? What would happen if you increase the pressure? If you could grab your hands, maybe not on a hot air balloon, but a regular balloon, squeeze the balloon, you squeeze it together, increasing the pressure does what to the density? Does it make the particles more compact or less compact? Good. It brings them closer together as you squeeze, so it increases the density. So with pressure, there'd be a direct relationship between increasing the pressure, increasing the density, because you squeeze them together. And last but not least, increasing the pressure would be like doing what to the temperature? Well, they're inverse, so it would be like decreasing it. If we cool down the balloon, now the air will come together and that whole balloon will sink. And that's what happens when they turn the heat off. Right? The particles come closer together. These changes with gases also apply to liquids and solids, but not to as great an extent. It's so easy to see air being heated up very quickly, whereas liquids and solids not. So matter has the maximum density. Which one's the most dense? Remember, density is how close the particles are packed together. So think about your models. Right? Which one are they closest together? Right? Hopefully you're thinking solid. Right? So for most things, solid is the most dense. Now, the next, they want you to put the phases of matter in order of decreasing density. Think about the word decreasing. Decreasing means to go down. So if you want to go down, do you want to start with the biggest or the smallest first? Good, the biggest. So start with solid, right? It's the most dense. So that's what you're going to fill in where it says first. Solid would be first. Draw a picture. Pause it if I'm going too fast. After solid, then you would put liquid next, because particles are kind of close together. They're just not all lined up and as packed as a solid would be. And then last but not least, the third would be a gas, because those particles are not dense. They're spread out. So that would be the least dense. Now water is the exception to that. Water is most dense when it is in the liquid phase. And you'd say, how's that possible? How come solid water, ice, the particles are all close together? Well, you probably already know this, that if you have liquid water and you put solid, instead of the ice being more compact, the ice floats to the top. Right? The reason for this is when water freezes at 0 degrees Celsius, the water expands. Those molecules expand outward. So when this water freezes, put it in the freezer, right? 0 degrees Celsius is what you need for the freezing point. That water will expand and it will freeze. The maximum density for water is not 0, but above 0. It's actually at 4 degrees Celsius. When you have like really, really cold liquid water, the greatest density is 1 or 1.0 gram per milliliter at 4 degrees Celsius. That's for water. What are some consequences of this? This is a spigot that I had coming through the foundation of my house. Right, it's supposed to be self-draining. Right, turn it off in wintertime and it drains, so you don't have a problem. Except it didn't work. It didn't drain. So in the winter there was water in here. That water froze. It expanded. And look what it did to this copper pipe. And this is tough. This is copper, and it busted it open. Another example. Bottle of soda. Can I take the bottle of soda and put it in the freezer? Not a good idea. You do not want to do this. Think about what happens to all that water. It freezes, it expands, right? It'll bust it open, right? And you're going to have sticky soda all over your freezer. Okay, to illustrate the concept, have you ever frozen water in a bottle? Right? See what happens? So if I take the bottle and I put a little bit of water in there, okay, not a big deal. I've done that before. I freeze it, and then next day I pull it out, I put water in the top, and I have like an ice cold water bottle that lasts me for most of the day. Not a bad idea. That's good. How about if I take the bottle and I fill it all the way to the top? All right, so that's right up to the top. Put the cap on it. Okay, let's see what that does. Good. Okay, so it's the next morning. Let's see what we got. So there's the bottle, frozen. And when I go to set it on the counter, see how wobbly it is? Actually, it doesn't even want to stand. Compare it. If you look up close, the bottom is recessed. This one is bulged right out, so the bottle can't even stand up. So you can see the ice has expanded the bottle. Whoops. All right. Part of the reason it hasn't busted the bottle is it's kind of like a soft plastic, so it has a little bit of give. I've had cases where it's a harder plastic and the bottle like breaks or cracks. So again, liquid water expands when it freezes. Some consequences of the fact that ice is less dense than liquid water rather than being a more compact solid, right? Because it's the exception. Ice skating, right? If it wasn't, you'd have liquid water, you'd have the ice in the bottom, and you'd be ice skating in like a puddle. Right? It'd be really weird. It floats in your soda. I don't know if that's a big deal and what it means, but that's what we're accustomed to. Here's a huge one, right? The idea that when the water freezes on the St. Lawrence River, right, or out in the lake, because it's less dense, it will freeze at the top. If it was like every other material, it would freeze in the bottom. Well, why is the big deal? Well, think about what lives in the river and in the lake. If it was actually freezing in the bottom, think about what would happen every winter to the fish, to the plant life. The fish would have had to evolve and adapt. They'd like swim south for the winter. They'd migrate. We know fish don't do that because ice is less dense. It freezes on the top and the fish and the plants can survive on the bottom. Busting pipes, we talked about that. That's a big business around here. People that winterize cottages so that doesn't happen. Ice fishing. A lot of people, probably you, might ice fish in the winter. Right? Wouldn't be able to do that if the ice didn't form on the top of the lake and the fish could survive underneath. Hockey, just like ice skating, right? A sport that they depend on the ice on the top of the surface.